Okay, up next we have Suzanne Berger, who's here to talk about the sandwich package. And I'll hand you over to her.
Okay, let's start. Yeah, welcome to the presentation. I present joint work with Achim Theilais and Nathaniel Graham with title Various Versatile Variances and Object-Oriented Implementation of Clustered Covariances in R. Well, this talk is mainly composed of two parts. First, I will discuss a set of computational tools providing for an object-oriented implementation of clustered covariances in the R package sandwich. And second, I will show a couple of results from a simulation study with the objective to assess the performance of clustered standard errors beyond linear and generalized linear models. So there is a range of popular strategies dealing with cluster dependencies in regression models, especially random intercepts are often introduced to capture unobserved cluster correlations, or as an alternative, generalized estimating equations are also able to account for such correlations. Another prominent approach, especially in econometrics and the social sciences, is to assume a quasi-maximum likelihood estimation that assumes a correctly specified score function, but a potentially misspecified remaining likelihood due to a lack of independence, as it is the case in cluster correlations. Yeah, well, this approach is known as quasi-maximum likelihood, leaves the parameter estimates unaffected, but adjusts covariances by using a sandwich estimator. And special cases of QML together with sandwich covariances comprise, for example, independent but heteroscedastic cross-section observations. These require HC heteroscedasticity consistent covariances, while autocorrelated time series observations necessitate heteroscedasticity and autocorrelated Heck covariances. And for clustered or panel data, clustered sandwich covariances are often employed. Well, there already are a couple of packages where various types of sandwich covariances are implemented. Standard R package is, for example, the sandwich package that calculates standard sandwich estimators. Sandwich package provides for an object-oriented implementation for the building blocks of the sandwich, which we will discuss later on in more detail, and model classes providing the necessary building blocks include, for example, the BDRX, CLM, Search, Hurdle, among many others. Well, for cross-section data, the sandwich function computes a plane sandwich estimate from a fitted model object as introduced by Eike Huber-White and defaulting to what is known as HC0. Week of HC is simply a wrapper to sandwich and computes general HC covariances ranging from HC0 to HC5. For time series data, function week of Heck computes Heck covariance estimates, and in addition there are further convenience interfaces, as for example for unused kernel Heck or for new West style Heck. But however, no clustered and panel covariances were available up to now in the sandwich package. But of course, different implementations for clustered sandwich covariances exist in R, but these are often scattered over various packages and often tied to LM objects or also dedicated model objects fitting certain linear or generalized linear models for clustered or panel data. So in a nutshell, there was no object-oriented implementation for cluster covariances in R that allowed plugging in different model objects from, in principle, any class, and using the implementation of multi-way Wyckoff as a starting point, a new and object-oriented implementation was established and integrated in the sandwich package, so that it's now possible to apply clustered covariances to more general models, including, for example, zero-inflated, censored, or limited responses. Well, covariance matrices of sandwich type are constructed as a meat matrix M between two slices of bread. A sandwich function relies only on a small set of extractor functions, namely estfun and bread, and calculates an estimator of the sandwich by multiplying estimators for the meat between two slices of bread. An estimate for bread is typically the empirical version of the inverse Hessian, and estfun returns the empirical estimating functions from a fitted model object. This is typically the derivative of an objective function, in most of cases the likelihood, with respect to a parameter vector. These are the scores in a maximum likelihood framework. On top of these extractor functions, different flavors of meat can be defined. Meat HC and meat HEC for the outer product, HC and HEC estimators for the meat, and all of these rely on the model just through the SFAN method. So for the new clustered and panel covariances, only new meat functions are in the end provided that ideally only extract the estimating functions from a fitted model object. And VCOV function then couples the meat with the bread estimate. Well, and I forgot to mention that for the meat HC, not only an SFAN method is needed, but also a model matrix method is needed for the decomposition of scores into working residuals times regressor matrix. So to sum up, the sandwich package has in the end extended along the same lines it was originally established. Well, and here we go. 1, 2, and multi-way clustered covariances with HC0 to HC3 types of bias correction are implemented in new function VCOV-CL for a fitted model object X. The essential idea here is to aggregate the empirical estimating functions within clusters and then compute an HC type covariance analogous to VCOV-HC for cross-section data. Yeah, the cluster argument then allows to specify either a cluster vector or a list or data frame of several cluster variables. If no cluster variable is supplied, then each observation is its own cluster, and thus the whole thing collapses to the basic sandwich estimator by default. Well, many publications just refer to the clustered standard errors, but actually there is a surprisingly wide variation in clustered covariances. That is particularly due to the different flavors of bias correction. And here the bias correction is composed of two parts that can separately be switched on and off. First is a cluster bias correction, which is controlled by the C-adjust argument, where the G is simply the number of clusters. And we have an HC bias adjustment, which is controlled by the type argument. Well, and yeah, here you can choose one of HC0 to HC3. The implementation of HC0 and HC1 bias adjustment, this is straightforward and can be simply added to the clustered meat matrix, but actually this is more demanding for cluster generalizations of HC2 and 3, because here the correction factors have to be applied directly to the working residuals prior to computing the clustered meat matrix. So HC2 and 3 bias adjustments are only available for LM and GLM objects, as they require computation of full blocks of the head matrix. So this is actually the only part that is not fully object-oriented. But beyond the GLM case, it's often not clear what the head matrix should be. Well, and last argument, multi-null. This is only for multi-way clustering, and I will skip details here for the moment. Well, for panel data, VCOV-PL is a new function that allows to estimate Driscoll and Gray and a panel version of new West covariances. Here the idea also is to aggregate the empirical estimating functions within each time period and then compute a HEC correction. Yeah, we have again a cluster argument that allows to specify a cluster or closer to the panel context a group or ID variable, and order by declares a time variable. If only one of order by and cluster is specified, then it is assumed that observations are ordered within the other variable. Yeah, and the weights in the panel sandwich covariance are set up by means of a kernel function along with a bandwidth or the corresponding lag, and we offer different kernels and lags that are provided. Yeah, last but not least, for panel corrected covariances, a la backend cuts are implemented in function VCOV-PC. Here we need again our decomposition of estimating functions into working residuals and regressor matrix, and then the idea simply is to aggregate the working residuals within each cluster, employ the outer product, and along with some further modifications. I will not go into details here. Well, the cluster and order by arguments have the same meaning as in VCOV-PL. And then we have a subsample argument, because estimation in balanced panels is here straightforward. But yeah, in the unbalanced case, the subsample argument allows to choose either a pairwise balanced sample or a balanced subset of the data. So details can be found in Bailey and Katz, for example. Yeah, so the main motivation for a new object-oriented implementation of clustered covariances in sandwich was the applicability beyond LM or GLM objects. And in the following example, I will make use of this object orientation and estimate clustered standard errors for count data hurdle model. So here we have data from Aguillon et al., and they investigated the effect of institutional ownership on innovation. Institutional owners are, for example, pension funds or insurance companies. And to capture the differing value of patterns, citation-weighted patent counts are used as a proxy for innovation. And this, of course, motivates the use of count data models. In their original analysis, the authors mostly employed a quasi-Poisson approach along with clustered standard errors. Well, a major shortcoming of these standard count data models is that zeros and positives are assumed to come from the same data generating process. But from an economic perspective, there is maybe a difference between first innovation and continuous innovation. So it can be the case that the first innovation is especially difficult to obtain in comparison to succeeding innovations. The rationale behind this is the notion of non-linearities in the innovation process. So does a company innovate at all? And if it innovates, how much innovation is there? Well, and in a reanalysis, we employed negative binomial hurdle models along with clustered covariances, which can now, with our new implementation, a lot more easier be obtained. Well, data, Agio et al. Data are also now in the sandwich package, and then a negative binomial hurdle model is fitted with the hurdle function from the counttrack package. And if we then compare our standard covariances as extracted from VCOV, which is typically based on the breadth estimate and relies on the assumption of a correctly specified model with independent observations. If we compare these standard covariances with basic sandwich covariances, and CL1 is our new clustered covariances with an HC1 type of bias correction, then we see that our standard errors do greatly overstate estimator precision. So for example, when you're looking at the last line, we see that our standard errors double from standard to basic sandwich standard errors, and even triple from standard to the CL1 to the clustered standard errors. Well, a more systematic analysis was then, of course, carried out with a simulation study, where again, the objective was to assess the performance of clustered standard errors beyond the GLM case. So the simulation design is as follows. A couple of response distributions are investigated among Gaussian, binomial with a logit link, Poisson, zero truncated, zero inflated Poisson, and beta responses. We have a linear predictor with a link function h, expected value mu, and with coefficients 0 and 0.85 for the intercept and slope parameters. However, these coefficients can be interchanged without affecting the results. Cluster correlation rho for the response is introduced via Gaussian cupola, and additionally, our regressor exhibits a within cluster correlation of 0.25. Each experiment is composed of 10,000 replications, each with 500 observations, consisting of 100 clusters with 5 observations per cluster. So we have already a huge amount of clusters here. And the outcome measure of interest is the empirical coverage of the 95% confidence interval for the slope. Here we go with the first simulation result. The performance of clustered standard errors for Gaussian, binomial, and Poisson response distribution here is examined. Along the y-axis, the coverage is plotted. Along the x-axis is the cluster correlation of the response. CL0, this is the clustered standard errors with HC0 type of bias correction, while PL and PC are the Driscoll and Gray and the panel corrected standard errors, all as implemented, introduced in the previous slides and implemented in sandwich package. CL0, of course, accounts for the clustering, but PL and PC are usually employed for panel data with a large time dimension. Standard and basic sandwich standard errors, well, they do not account for the clustering structure, but random here, these are standard errors from a random intercepts model, and GE, these are the standard errors from a generalized estimating equation with an exchangeable correlation structure. They do account for this clustering structure. We see that for the Gaussian response, the underestimation of standard errors gets even more pronounced with an increase in cluster correlation for some methods, while some other methods perform well. Well, the aim here is to reach a value close to 0.95 of the coverage. Values below are considered to underestimate standard errors, while values above considered indicate toward a conservative bias. And compared to the Gaussian response, results are qualitatively similar for binomial and logit Poisson responses, except for the standard errors from the random intercepts model. What we see is that standard and basic sandwich standard errors, they are underestimated. The more, the higher the cluster correlation. This is, of course, no surprise, as these methods do not account for the clustering structure. But our clustered standard errors and even our GE standard errors, they perform well for all cluster correlations, even in cases of high cluster correlation. And of course we have our standard errors from the random intercepts model, and here these perform only well for the Gaussian response, but do something else for the binomial and Poisson responses. We'll not go into detail here, but this has to do that here a bias is introduced in the end. And the poor performance of our panel-corrected standard errors, and of course, especially our Driscoll and Gray standard errors, this depends, of course, on the short time dimension and on the correlation structure chosen for our copola. If we do the whole simulation again with an AR1 correlation structure and with a longer time dimension, then even these methods perform quite well. Okay, and further results here, we have a look at the performance of clustered standard errors for beta regression, beta distribution, zero truncated Poisson, and zero inflated Poisson distribution. Well, a similar picture emerges as before. Clustered standard errors perform quite well for all response distributions and cluster correlations. Here, consider the changed scaling of the y-axis. So here we have an error scale. But again, our standard and our basic sandwich standard errors, they are underestimated the more the higher the cluster correlation, which is, of course, no surprise. As I already said, these do not account for the clustering structure. Well, all I've told you now is already on RForge, and hopefully it will be on CRAN. And the manuscript on which this talk was based is also included as a vignette in the sandwich package, in addition to the whole simulation stuff. Well, thank you.